So just to round out what we were talking about last time, we were talking about all these nonlinear problems, and I told you that for nonlinear problems, what you are usually trying to solve is a system of nonlinear equations that just looks like internal force minus external force is 0. And this is a vector equation. So, and the most common method that we use to solve these types of equations is the Newton's method. So, uh, all that you're trying to do in the Newton's method is to try to calculate the tangent matrix, and you keep on updating your solution uh, with this increment that you calculate from with respect to your assumed solution. So the idea is you assume a solution, calculate the tangent matrix at that point, calculate the residual at that point, and calculate the increment. And you keep on repeating this loop over and over until you hit, you are within some tolerance. So this is also what Abacus uses in its step module. If you've used the general static step, this is what Abacus does. But there's also a different type of nonlinear step in Abacus that they call static RIX. And the RIX method, what that does is that it takes these types of small increments. So for example, this is the displacement versus residual, or displacement versus load curve. And instead of applying all the load at once, I think if you, those of you who are using nonlinear methods for in Abacus, there is a option, or there is a box when you set up the step where you have to choose the initial step. So by default, in Abacus, the initial step is set to 1. What that means is that you are applying all the load right in one step. So for nonlinear problems, whenever you apply all the load in one step, it can have some problems. So there is an option to set the initial step to be something like 0.1 or 0.05. What that means is you're applying only 5% or 10% of the load. And then Abacus will just keep on increasing the load level, going from one point to the next. And within each of these cycles, it will do the nonlinear iteration. So it will do all these steps for this load, and then do all those steps for this load, and so on, keep on going. So also those of you who are using the nonlinear Abacus methods, if your problem has some kind of an instability, meaning that if you reach a maximum point and then you start to decrease the load, in that case it is better to use the static RIX method. So the RIX method always makes these types of cuts along the equilibrium path. So the RIX method is used whenever your problem has some kinds of instabilities. So just to give you an example, last time we weren't able to run this thing, so hopefully today we'll get to do that. So the idea is that this is a cantilever beam. It is fixed. It is not fixed. It is attached to a soft spring on the left end, and we are applying a moment, a bending moment here on the right end. And we are going to apply that bending moment in small steps, just like the RIX method. So what happens when you apply this bending moment here, the beam starts to bend, and at a certain point, the spring here is not able to sustain the load, and at that point you have a instability or buckling. So so let's see how that comes about. So here you can see that these are the Newton iterations that are going on, and the residual also, which is being plotted here. So I'll keep this window here. And so initially the beam starts out at a straight location, and now you are increasing the moment here. This is the deflection on the x-axis, and on the y-axis you have load. Load meaning the moment that is being applied. Yeah. Mm-hmm. Yes, right. So whenever the minimum eigenvalue of the stiffness matrix goes negative or goes to 0, at that point you have instability. So, and that will happen because this is a geometrically nonlinear problem. The geometric stiffness can either stiffen up the member or it can either make it unstable. So even in even for the linear problems, when we are talking about eigenvalues of the element matrix, those eigenvalues which are 0 represented rigid body modes. So having a rigid body mode is also some sort of an instability. So so let me continue this analysis. Oops. Okay. And I just want to show you that in this case, Abacus also does something similar for the Rix method. You can see that the length of these steps, that is the amount of load, as I keep on applying more and more moment, it is adapting to the amount of moment. So now you can see that it's about to reach its final moment capacity and it's about to go unstable. So the steps start to become smaller and smaller. And at this point, there's a lot of compression here, tension here, and at this point, the beam does start to go unstable. So this showing that this curve is starting to decrease means that your displacement is increasing while your load is decreasing. So that's an unstable behavior right here. So and now this beam is going to snap around. So you can imagine this is a rubber beam, and if you keep on increasing moment, at some point it will snap. So, and it will start to take all that load in the opposite direction. But just to tell you that even in Abacus, if you are using nonlinear procedures, Abacus might compute to quite a long distance. And then if you finally get that Abacus failed to converge or something, that doesn't mean that the entire analysis is a waste. It just means that Abacus computed to some point, but then at the final point it was not able to recover or not able to converge. So you would still have the results from all those points, even if the final result, even at the final point, if Abacus is not able to converge. So here also, I think in this problem also, this is obviously a very basic code, so it also has some convergence problems. And I think very shortly you should see that it will fail to converge. Okay. So you can see now that it did at the 82nd step. In this problem, I had defined that this should take 100 steps, but at the 82nd step, it did 10 iterations, and the residual did not converge. You can see from earlier problems that the residual started out very big, but then it got down to a small number with respect to the original. So if you are using something like 10 to the power minus 4 or 5 as your tolerance for the residual, this is convergence. And just like I told you, 4 or 5 iterations is what Newton's method takes to converge. But in this case, the residual does not seem to be converging, and finally you get some absurd state, and at that point Abacus would also tell you that the iterations did not converge. But it doesn't mean that the entire analysis is waste. You still have results. If you click on results, you can still plot all the way up to the point where it was converging. So that's just something for you to keep in mind. All right, so let's get back to what we were talking about with beams. Um, Um, all right, so for the beam theory, we said that if we have a two-dimensional or three-dimensional object, to be able to analyze that two-dimensional or three-dimensional object with beam theory, we are going to assume a certain deformation map. So we are going to say that we will express the deformation of the beam with respect to the cross section or the centroid line, and in addition, that cross section can rotate with respect to the centroid line. So every cross section is rigid, but if you tell me where the centroid line goes, and if you tell me what is the rotation of the cross section, then that completely defines the deformation of the beam. And with this assumption, if you draw a small section of a beam, you can write out the equilibrium equations for axial equilibrium, transverse, and moment equilibrium. This is something that we have seen long back. Um, we also saw that there are two types of beam theories. One is the Timoshenko beam theory, that is for deep beams where shear deformation is important. And the other one is Bernoulli-Euler beam theory, where we assume that the beam is going to be rigid in shear. So in the Bernoulli-Euler beam theory, we do not have any shear displacement, and we assume that um, that W prime, W prime is the angle that the centroid line makes with the x-axis, and that is going to be equal to this theta, and theta is nothing but the rotation of each of those cross sections. So these are the governing equations, and we took a look at how we can set up the weak form. So if these are the governing equations for the Timoshenko beam, which includes shear, we have three equations. We took a look at some boundary conditions for the shear beam, and finally, when we have to set up the weak form, all that we do is take the governing equations, multiply them with their virtual counterparts, virtual displacements and rotations, and just integrate over the domain. So, so let me ask you this: what if I were to take all these equations and multiply them with some scalar, right? Why should I just have this integral plus this integral plus this integral? Maybe I can say alpha 1 plus alpha 2 times this plus alpha 3 times this. So would that be a different formulation, or would we get the same result? So if we take this weak form, and if we just multiply these three different terms with different scalars, all that we are doing is finally, when we get our kd minus f, we are taking some of those equations, multiplying with a different scalar, some other sets of equations with a different scalar, and this equation with a different scalar. So what that means is, so if you have a system of equations, if you take some equation, multiply it with a different scalar, that doesn't change the underlying system of equations, right? So you can multiply these equations with any scalar, and people sometimes do that to make the condition number of your matrix a little better. So so essentially, this is how you would set up the weak form. And we took a look at this example with the Ritz method for cantilever beam. Similarly, for the Bernoulli-Euler beam, the bending equation and the transverse equation get coupled together. We actually lose the ability to enforce the shear equation, and the axial equation is decoupled anyway. So there is this axial equation which is separate, and this bending and transverse equation which is separate. And now to solve a Bernoulli-Euler bending problem, all that you have to do is to solve this equation. So we also, I think, did some problems on this. And finally, if you do the integration by parts, take the governing equation, multiply it with virtual displacement, integration by parts, you get this as the weak form. And I told you that the difference between one of the important difference between the Bernoulli-Euler and the Timoshenko beam is that um, when you are writing out this weak form, in the weak form for the Bernoulli-Euler beam, you have these double derivatives, which means that the space of functions that we choose for for W in Bernoulli-Euler beams has to satisfy H2 0, meaning that if you take any function in this case, if you take any function for approximating W and you take the second derivative of that, that has to be square integrable. So these functions, they are not square integrable. The second derivative is not square integrable because you can see that the derivative at this point has a discontinuity. Even the derivative at this point has a discontinuity. So if you take the derivative of this red line, there is going to be an infinite number right here, and that is unacceptable for H2. So the same shape functions that we were able to use for one-dimensional problem when we were doing with H1 space, now you cannot use those. So so another example for the cantilever beam in this case, we saw that, and I think this is something that you did in class. All right, so this is about where we had stopped for when we were talking about beams, and essentially for beams also we have some variational principles. We started with these governing equations, and if you write these out to construct the weak form, you use either the method of weighted residuals or the principle of virtual work. To go from, or alternatively, what you can do is start from an energy functional and calculate G. And to do that, we had to minimize using the Gettier derivative. How about from here to here? What does that mean? If I have a weak form, can I construct an energy functional? Using the Weinberg theorem, you can construct the energy functional, and going from the weak form back to the governing equations, that is the Euler equations that I had asked you on even on the midterm. So what I had given you was some energy functional for a scalar problem on the heat conduction thing, and then you minimize it and do a unbalancing of the derivatives, and you get the governing Euler equations. So Euler equations. All right, so we see that we can write the Bernoulli-Euler beam energy principle like this. So let's see what happens when we minimize it. So to minimize it, we are going to take the Gettier derivative of this function in the direction of a virtual displacement. So the virtual displacement is W bar. And this Gettier derivative is defined as d by d epsilon of the same energy functional plus small perturbation in the virtual direction. So what we are saying is you take the original displacement, multiply or add a small virtual displacement to it, and then take its derivative with respect to epsilon. After you take the derivative with respect to epsilon, set it equal to 0. So this is what the Gettier derivative, this is how it is defined. And if you do this for this particular functional, what you should get is EI W bar double prime W double prime. So this is nothing but the moment times the virtual curvature, dx plus integral 0 to L W bar times Q minus W bar times M prime. This is also dx, and then minus W bar times Q. This is the applied load at 0 and L minus W bar prime times M. So all these terms, these last two terms, they come from the boundary condition. If you have end loads applied on your beam, or if you have end moments or end loads applied on your beam, this is the applied distributed load along the beam, Q and M prime, and this is the bending energy, internal energy stored, internal virtual work stored in the beam. And this is precisely equal to the GU or GW times W bar for the Bernoulli Euler. And finally, you will take this and do your finite element approximation and set up your linear equations. So let's see how to do that. And this is on today's handout. So first we'll consider the Timoshenko beam that includes shear. And just like I told you that the weak form for the Timoshenko beam is this. And if you remember from our two-dimensional problems or one-dimensional problem, once we set up the weak form, all that we need to do is plug in expressions for U or W and theta, and just follow the algebra to set up our equations of equilibrium. And so let's take a look at this weak form. You can see that the highest order derivative for any term, for U, highest order derivative is 1, W it is 1, theta, the derivative is 1, which means that we can still use H1 space. So all that we need to do is to make sure that our functions that we choose must be continuous. So here is a little example of the type of choices that you could make. So just consider a simply supported beam, and there is this distributed load that is acting on it, and we are going to discretize this beam with these different elements. So let's say there are these 5. We discretize this beam with 5 different elements. So for the one-dimensional problem, if you remember, we used these shape functions. Within any element, you can use these shape functions to interpolate the axial displacement or the transverse displacement. So we are going to use the same shape functions to interpolate axial, transverse, and rotation. All 3 quantities are going to be interpolated with the same type of shape functions. And we already know that if you assemble these equations, what the shape functions that you get would be something like this, the hat shape functions that start here 0, go up to this point, go back to 0, and like this. So clearly this shape function is continuous. And if this is continuous, then it belongs to the H1 space, which is a valid choice for all 3 of them. So what happens when we choose these shape functions is that for any particular element, you are choosing that the degrees of freedom for that element are going to be axial displacement at node 1, transverse displacement at node 1, theta, rotation. So there are 3 degrees of freedom per node whenever you choose a Timoshenko beam. Okay, and the element degrees of freedom I've just listed out here. You have U1, U2, which are axial displacements, W1, W2, they're transverse displacements, and theta 1 and theta 2. And these theta 1 and theta 2 represent the rotations of these cross sections, which can be independent of this W. So once you make these approximations, you've said that U is equal to N times D, and you take that U is equal to N times D and go back and plug it up into all these terms. Everywhere that U occurs, you substitute that expression N times D, W prime, theta, and all those terms. All that you have to do now is to plug in the expression for these and its derivatives. So ultimately, when you do that, it will lead to the same old equation, and where you can calculate all these, the global stiffness matrix, just by assembling all these element stiffness matrix, just the same way that you had done for your one-dimensional problem or for your two-dimensional problems. Um, so let's carefully look at what an element stiffness matrix looks like for a beam element. So we are talking about this Timoshenko beam element. And now this beam element has 3 degrees of freedom per node for a total of 6 degrees of freedom. Um, and let's see what these element stiffness matrices come from. So let's consider this term first. This is the same term that we had for our one-dimensional problem, u bar times EA times, u bar prime, EA, u prime. This is the term that was also there in our one-dimensional problem, and this is the term that leads to KUU. So when you write this out, you will see that your element stiffness matrix will turn out to be a 6 cross 6 matrix. And those degrees of freedom are those 6 degrees of freedom. Each one of those submatrices is going to be a 2 cross 2. And that's how you will construct this element stiffness matrix for a beam element. So the KUU is coming from the axial term, and you can see that it is not even coupled to the bending and transverse. So this problem you could solve completely independently of the bending and the transverse problems. And if you remember from the one-dimensional case, the stiffness matrix that you got for the one-dimensional case was n prime or C times A or E times A times this n prime transpose, and that led to this element stiffness matrix. Similarly, for KWW, where do we get this from? So the KWW term comes from this W bar times GA times W prime. Okay, so this W prime times GA times W prime is what leads to that KWW term. Similarly, we will have KW times GA times theta. That's the KW theta term. And similarly, we'll have K theta theta term. One from here and one from here. So this is what the element stiffness matrix looks like for a Timoshenko beam. And the element force vector, that is going to be coming from all these terms. So again, you are going to substitute U bar is equal to N times D times the axial load, transverse virtual displacement times the transverse load, and applied moments. And if you do that, you can express N transpose times F. This is very similar to what you had this is N transpose times this term, N transpose times this term, and N transpose times this term. So this is basically how you would construct an element stiffness, element force vector. You can also use higher order Lagrange shape functions for this. So what we just talked about all this way, this was for the linear elements. When you choose 2 nodes per element and you use linear shape functions, if you use higher order shape functions, for example, if you have 3-noded element, in that case, your shape function matrix, it will just be a function of n1, n2, n3. And you would have how many degrees of freedom for the element? There will be a total of 9 degrees of freedom per element, because you have displacement in the 2 directions at this node and rotation. So every node has 3 degrees of freedom. If you have 3 nodes, you have 9 degrees of freedom per element, which means that what would be the size of this? 9 cross 9, and each one of those is going to be a 3 cross 3. So essentially, you can keep on increasing the number of nodes within the beam elements. All that you're doing is approximating this U with some shape functions times the nodal degrees of freedom. So this is something that that is common to all these different finite element formulations. But so like I told you also when we were talking about Ritz method, if you use the same order polynomials, so for example, here we were using linear polynomials for u, for w, and for theta. That causes some problems. So even in the Ritz method, we chose that w is going to be interpolated with a quadratic polynomial and this with a linear polynomial. And we do that so that when we take the derivative of w, it is of the same order as theta. So if you use the same order polynomial for w and theta, then it causes some problems, and those problems are called the shear locking problem. So we try to not use this w and theta of the same order. We try to use w which is one order higher than theta. So people have done some tests on this, and what does this shear locking mean? Um, it means that if you go back to this problem of the simply supported beam, if you apply this load and if you use equal order interpolation, the amount of deflection that you will get for the beam will be very small, in fact almost close to zero. So the beam becomes extremely stiff, and those types of problems are called locking. So essentially what this means is that the element stiffness matrix that you calculated is very, very stiff, much stiffer than what it should be. Those types of problems are called locking. When the element stiffness matrix is much stiffer than what you have, it's called locking. If it is much softer, then it is instability. So if the element stiffness matrix is much softer, you get instability. If it is much stiffer, then you get locking. Okay. Um, so the couple of ways to get rid of this shear locking for Timoshenko beams is one of those methods is called reduced integration. So this is also something that we've seen before, but not maybe in the context of beams. Um, Essentially, the idea is that we will choose equal order interpolations for w and theta. But when we are integrating the shear term, what we are doing is we are integrating along the length of the element. We will choose an interpolation order which is appropriate for w. So if you remember, if you use equal order interpolation, let's say linear and linear, linear for w and linear for theta, in that case w prime would be constant, theta would be linear. W prime is constant, theta would be linear. Um, so in order to integrate this term exactly, what would we need? Linear times linear. We need to integrate quadratic terms exactly. And to do that, what number of Gauss quadrature should we use? If we have a quadratic function, how many Gauss points would we need to integrate it exactly? 2 Gauss points for a quadratic. So if we want to integrate theta exactly, we would need 2 points. But if we want to integrate only w prime exactly, which is a constant times constant, so we can integrate a constant function with just 1 Gauss point. So even though we know that theta needs to be integrated with 2 Gauss points, we will deliberately choose only 1 Gauss point, and that is what reduced integration does. So if you do that only for the shear term, that fixes the shear locking, and that makes your stiffness matrix soft enough so that you will get good results. Um, so even for, just like in the continuum problems, even for these structural problems, reduced integration does have some benefits. So similarly, if we use equal order interpolation for w and theta for quadratic and quadratic, what would be the highest order polynomial if we use quadratic and quadratic? Theta times theta, that would be order 4, and we would need 3 Gauss points to integrate it exactly, because 3 Gauss points would integrate up to order 5 exactly, right? 3 times 2 minus 1. But if we have a 4th order polynomial, we would need 3 Gauss points. On the other hand, for this w prime would be linear. Linear times linear would be quadratic, and we would need only 2 Gauss points for that. So again, we deliberately choose less number of Gauss points, even though we know that we are making some errors here. Those errors are helping us to make our stiffness matrix softer, and that gives us a little better response and in terms of locking. So the second way is to get rid of shear locking is called consistent interpolation. And essentially what we do in this is we choose our shape functions in such a way that w prime and theta, they are of the same order. So instead of choosing quadratic and quadratic and or linear and linear, what we choose is quadratic and linear, meaning that if you take w prime, then this would become linear and these two would have the same order. So what does this look like? If you choose quadratic for quadratic shape function for w, those would be these types of shape functions. These are quadratic shape functions. So in this case, the element degrees of freedom, they have a little different structure. So element dots, they have a little different structure. You have u1, u2, you have w1, wc, which is the center node, w2, theta 1, theta 2. So these are for the axial component, these three are for the transverse component, and these three are for the these two are for the rotational component. And if these are the element degrees of freedom, what would be the size of my stiffness matrix? So the size of the stiffness matrix would be 7 cross 7. Element stiffness matrix is going to be 7 cross 7, and the structure of that stiffness matrix would be very similar to what we had before. You have KUU here, KWW here, K theta theta here, KW theta here, and K theta W here. So what would be the sizes of all these? KUU would be 2 cross 2, because that doesn't change. We are still using linear shape functions for U. KWW would be 3 cross 3. KW theta would be 3 cross 2. And similarly, K theta W would be its transpose, which is 2 cross 3. And finally, K theta theta would be 2 cross 2. So even when we use different order interpolations for W and theta, we can construct a square stiffness matrix, even though individual terms might actually be rectangular. And these type of element, this is called a consistent interpolation element. This does not show shear locking. So you can go ahead and integrate your element stiffness matrices with your full integration, and it will not show shear locking. So that's how you would construct element shape functions for Timoshenko beams. And this is nothing different from any other one-dimensional problem. There was no problem because the highest order derivative was 1. So all our shape functions that we used for the one-dimensional problems were applicable here. But for the Bernoulli-Euler beam, the situation is a little bit different. In this case, you can see that in the weak form, the highest order derivative is 2, which means that we must choose functions which have second derivatives that are square integrable. So not only the function itself needs to be continuous, its derivative needs to be continuous. So, so in order to construct these types of shape functions, what we do is, let's take a look at what we did for the one-dimensional problem first. So here what I'm showing you is just a cantilever beam. We are going to discretize that beam with 4 elements here. And the analogous problem that we did long back was this one-dimensional problem, which again we are discretizing with 4 elements. And now we want to construct the shape functions for this one element. So for finite elements, when we constructed the shape functions for this one-dimensional element, what we said was we are assuming that the solution between these two nodes is linear. Okay, and if we are assuming that the solution between these two nodes is linear, then we can express it as this type of a polynomial. But just to make sure that the solution is continuous throughout the domain, what we did was that we enforced the condition that the displacement computed from this expression at this node should be equal to the u1 degree of freedom, and displacement computed at this node from this expression should be equal to u2. That's the underlying concept of finite element. This is basically saying that we are going to interpolate the displacement between the nodes with linear polynomials. So if you use these two conditions, let's take a look at the first condition. U1 is equal to this expression where x is this value. So what we are saying is, take a look at this first equation. U1 is equal to A0 plus A1 times x E1. So essentially we're saying that U1 is equal to this thing when x is here. U2 is equal to A0 plus A1 x2. Again this equation at this point. And that gives us two equations and two quote-unquote unknowns where you can solve for these unknowns by inverting this matrix. So the unknowns are these A1 and A0 and A1, and when you do that, you can express these shape functions as n times d. So this is how we constructed the shape function for one-dimensional elements, and this is also something that you did for your triangular element. In triangular element also we set up this type of an equation to find out what the shape functions were, right? In the triangular element you had 1 x1 y1, 1 x2 y2, 1 x3 y3. So the same type of thing we did for one-dimensional thing. But now for the Bernoulli Euler beam, the situation is a little different. If you consider one element here, not only do we need to enforce that the displacement matches, but also that the theta, that the rotation at the nodes also matches. So the conditions, we will have a total of 4 conditions, meaning that displacement and rotation at this point, displacement and rotation at this point. And since we have 4 conditions, we need a 4th order, 4 parameter polynomial. So the least order polynomial with 4 parameters is going to be a cubic, and we can write that out as A1 plus A0 plus A1x plus A2 x square plus A3 x cube. So this is the minimum order polynomial that you can use for Bernoulli Euler beams, the cubic polynomial. And the conditions are W1, which is this displacement at node 1. This is the degree of freedom, should be equal to A0 plus A1 x E1. So if I give you the locations of these 2 points, let's say this is at 3.4 and this is at 4.3. So you know the values of these 2 things. These 2 are constants now. The locations or the coordinates of these elements, they are constants. So you can plug in those constants here, and you can write out the expression A2 x E2 square plus A3 x x E1 cube. So essentially what this equation is saying is that if you calculate the displacement at this point, it should equal to the degree of freedom here. So similarly, you will have theta 1, which is derivative of wx, because we have that theta is equal to w prime is equal to a1 plus 2 a2 x plus 3 a3 x square. So that's theta, and the second equation just becomes then A1, let me write it a little differently, A1 plus 2 A2 x E1 plus 3 A3 x E1 square. And similarly, you will have W2, which is displacement at the second node. That gives me A0 plus um, A1 x E2 plus A2 x E2 square plus A3 x E2 square or cube, and theta 2. So each element for a Bernoulli Euler beam, instead of having 3 degrees of freedom per node, it has 2 degrees of um, two. Well, actually, if you include the axial displacements, then it does have 3 degrees of freedom. But and then finally you will get 2A2 x E2 plus 3A3 x E2 square. And if you were to write this thing in the matrix form, you would get W1 theta 1, W2 theta 2. These are the element degrees of freedom, is equal to um, you can calculate terms here, 1 x E1 x E1 square x E1 cube and so on, and what you would have here is A0 A1 A2 A3, and you can invert this matrix. You can invert this matrix to calculate what these things will be, and I'll tell you what the final form is maybe next time. All right, so see you on Friday.